The purpose of this lab is to analyze the motion of a falling object. For my object, I chose to use a packet of gum, which has a mass of approximately 30 grams. I took a video of myself dropping the gum, then analyzed the motion in Tracker. My video was rotated 90 degrees, but that did not affect my results. I simply aligned the coordinate axes in Tracker to the object's motion so that it fell in the negative y direction. I also measured the side of the gum package and entered that length into Tracker as a calibration stick. To create my model, I entered my information into VIDLE. I put in a mass of 0.03 kilograms and an initial position and an initial velocity of 0. I set G equal to 9.8 for the gravity, and the total force on the system is negative G times the object's mass times J hat, which is the unit vector for the y-axis. This means that the only force acting upon the object is the force due to gravity. Here is the resulting graph, with the model in red and the experimental data in blue. As you can see, the model graph overpredicts the object's motion. That is, the package of gum did not fall as far as the model predicted it would. This is because I had left out an important force acting on the object, the drag force. The drag force pushes in the opposite direction to the object's velocity. This means that the drag force on the gum pushes it upwards, causing it to fall slightly slower than it would if only gravity were acting upon it. The formula for turbulent drag is b times the magnitude of velocity squared. I plugged this information into VIDLE so that the net force now equaled the force due to gravity plus the drag force. However, I didn't know what to enter in my equation as the value of b. To find out what b was, I entered different values until the final predicted position in the updated model matched the actual final position from my data. The b value that caused this turned out to be 0.0052. Here is the model in VIDLE, where the large yellow arrow represents the force due to gravity, and the smaller blue arrow represents the drag force. Here is the final graph, which shows the object's experimental position and two models, one with drag force and one without. The model with the drag force fits the experimental data very well. This is mainly because I adjusted the value of b so that both graphs would have the same final value. However, even with this manipulation, the model graph very slightly underpredicts the position of the object in the middle of the graph. There are a few possible sources for this error. One is that the mass of the gum package was never confirmed, only approximated using the nutrition information given on the back. Another is that the length scale used in Tracker was from the measurement of the side of the gum package. Since this is such a short length and I was holding the gum at a slight angle, the length was difficult to put into Tracker accurately. Next, I investigated whether either model predicted that the gum would eventually travel at a terminal velocity. An object reaches terminal velocity when the drag force becomes great enough to equal the force due to gravity. That means the net force would equal 0, and the object would fall with a constant velocity. To find out if the models predicted this, I simply let VIDLE run the two programs for a longer time than they had before. I chose a time of 2 seconds. Here is the resulting graph. As you can see, the velocity of the model with no drag keeps increasing, but the model with drag reaches a terminal velocity. This is because the model with no drag can only keep accelerating, since there is no force slowing it down. Next, I made a model of what would happen if I threw the package of gum downward, rather than let it drop. In VIDLE, I gave the gum an initial downward velocity of 3 meters per second. Here is that graph, along with the original graph with no initial velocity. Both models include drag. It turns out that both models reach the same terminal velocity. However, the model with the higher initial velocity reaches the terminal velocity first. Thank you for watching.